When you build systems across multiple servers or rely on external APIs, network failure is a constant reality. A user clicks a button, a connection stutters, and the system registers a harmless 2-second timeout. The instinctive coding response to a failed request is to write logic that tries again immediately. If the database doesn't answer on the first attempt, the application is programmed to instantly knock on the door a second time. Now scale that scenario up. Imagine 1,000 independent clients hitting that exact same micro-outage simultaneously, and all 1,000 are programmed to instantly execute that exact same unconditional retry loop. Treating a sprawling distributed network like a perfectly reliable local machine takes a routine data hiccup and transforms it into a system-wide threat. The exact moment the server catches its breath and comes back online, it is instantly bombarded by the synchronized immediate retry requests from all 1,000 clients at once. This chart shows a standard server load limit. That horizontal line represents the maximum healthy operational capacity. When the server recovers, the normal traffic volume is completely eclipsed by a massive vertical spike of artificial retry requests. The sudden volume pushes the system load well past 100%, and the backend collapses. Engineers call this a retry storm. The application has executed an accidental, self-inflicted denial-of-service attack against its own infrastructure. High-scale architecture incorporates internal constraints to prevent eager components from cannibalizing each other during a momentary slowdown. To fix the storm, architects introduce a mathematical intervention. Instead of firing retry requests immediately, they force the system to systematically pace its traffic. This timeline illustrates a strategy called Exponential Backoff. Instead of a constant barrage, the client is programmed to wait 1 second before trying again. If that second attempt fails, it waits 2 seconds. Then 4, then 8, progressively doubling the delay. By explicitly spacing out the retry traffic, this algorithm gives an overloaded server the physical time and network bandwidth required to clear its massive backlog and stabilize. Surviving network bottlenecks requires hard-coding structural patience directly into the architecture. But if thousands of clients happen to be rejected at the exact same millisecond, a hidden mathematical flaw in fixed-interval backoffs immediately emerges. This diagram tracks multiple clients using standard exponential backoff. Because they all failed simultaneously, they execute their retries at the exact same moments. They hit the server together after 1 second, again at 3 seconds, and again at 7. Without variation, the algorithm just delays the retry storm. To permanently break this dangerous synchronization, developers introduce a concept known as jitter. Jitter injects algorithmic randomness into the delay. Instead of waiting exactly 2 seconds, a client might wait anywhere between 1.5 and 2.5 seconds. This scatters the retry attempts across a wider time window, flattening those severe vertical spikes into a smooth, manageable wave. Perfect order and synchronization in a distributed network is lethal. Controlled, algorithmic chaos is necessary to maintain system stability. Pacing the network traffic protects the server hardware, but it introduces an entirely new problem for data safety. Imagine an external payment gateway that times out while processing a transaction. If the original payment actually succeeded, but the confirmation response was dropped by the network, executing a retry algorithm will blindly submit the exact same transaction again. The system recovers, but the user is double charged. This flowchart demonstrates idempotency. It is a structural design rule guaranteeing that repeating a command 10 times produces the exact same state as executing it once. By attaching a unique ID to the initial request, the server recognizes the repetition, hits a duplicate detected logic gate, and returns a success message without reprocessing the payment. While AI tools can generate functional logic in seconds, they rarely implement these non-functional safety nets by default. In a standard prompt to build a payment handler, an AI will prioritize the success path of the transaction, but frequently leaves the idempotency key and retry limits entirely out of the code. Relying on those defaults creates a fragile system that works in a local test, but fails under real-world network stress. Fixing network traffic flow is completely useless if the resulting retries quietly corrupt the underlying database. Safe repetition absolutely requires idempotency. An amateur coding mindset assumes the network will always succeed and panics when it inevitably stutters. A professional architect assumes unreliability and designs the system to handle failure first. We took a destructive, naive retry loop and evolved it into a resilient architecture, combining the pacing of exponential backoff, the controlled chaos of jitter, and the safety of idempotency. The system handles errors safely. True scalability defines how a system handles stress, prioritizing core features and managing localized failures to prevent a total self-destruction. A successful retry is an act of intelligence, not persistence. But even the smartest retry logic has limits. When local errors slip past these safety nets and trigger chain reactions across separate services, the system faces a different kind of threat. We'll map out the mechanics of cascading failures in the next episode.